Hey, I'm Tom and I'm a PhD student at Lancaster University in the UK. Today I will be virtually presenting my paper on CollabAR, investigating the mediating role of mobile AR interfaces in co-located group collaboration. AR is becoming a lot more ubiquitous, with research and businesses pushing this technology. Modern mobile AR allows users to pull out their personal device, like a mobile phone or a tablet, and augment virtual objects onto the real world, which introduces many new opportunities for AR design. There are many tools out there that allow this interaction already. This handheld mobile AR is naturally collaborative. When users are co-located, the distributed view of the same object opens opportunities for people to work together. However, lots of current AR applications are only built specifically for individuals. While some applications do allow some form of implicit co-located collaboration, this isn't the main focus. And there is a lack of operational consistency, shared objects, and interfaces, which means that most interfaces are on the actual screen and tethered to the device. There are no interfaces designed to show that collaboration is actually happening. And fundamentally, there is a lack of studies and insights, with very little research into how AR specifically is enabling co-located interaction. Current related work that exists are separated into two categories. There are many examples of co-located interaction without the use of AR, and there is also work around collaboration in AR in general. However, there is a space between the two which is underexplored: the natural collaboration of co-located users utilizing mobile AR. So the question we asked ourselves was, how can we build a systematic understanding of existing group dynamics and practices in co-located ad hoc situations? We aimed to answer this question by codifying collaborative practices into three sets of group dynamics: collaboration styles, context switching, device handling and manipulation. To do this, we designed a simple mobile AR interface, and then conducted an observational study to provide insights on how groups of 4 people collaborate using this interface. So the example AR interface we created used basic gestures to manipulate models. The user would tap the screen and drag their finger to rotate the model. When the user taps the screen, a clutching mechanism locks the model, meaning only one user can manipulate the model at any time. To visualize this locking mechanism, each user is assigned a unique color. This displays as a border when clutching the screen. If they are the current holder of the lock, their color is displayed for all users to see. In these images, you can see 3 states of the application, with the left being no marker is found and no model is displayed, and the right being the user locking and rotating the model. The Rubik's Cube you see in these images was part of 6 models we created, which were abstract examples of objects that exist in some application areas of AR. For example, in the middle left, we see a DNA helix, which is an abstraction of what could be found in educational situations. And in the bottom right, we see some houses, which could represent virtual models for architecture. We designed these models to have different levels of complexity. We considered the scale, geometric shape, density of colour and subshapes, and intricacies. We recruited a total of 20 participants and asked them to complete a set of 3 tasks for each level of model complexity, so 9 tasks in total. We recruited participants using a snowball sampling method, so all the participants knew at least one other person in their group, if not all of them. Out of the 3 tasks per level, the first and second task were to inspect the model. An example of an inspect task was to count how many red tiles are on this cube. The third task was to compare 2 different models of the same level of complexity. An example of a given question was comparing the third and sixth model, list the colours that do not appear in both models. We collected data through video recordings, notes, NASA TLX questionnaires, and a group interview. And we coded this data specifically looking at collaboration practices, participants' interactions with each other and with their device, and how they handled their devices. We coded participants' interaction with each other into the following collaboration styles: active discussion, which was the face-to-face discussions including all participants, through to distributed view, where participants would focus on their own device while still continuing the conversation in the group. In our results, we examined use patterns, usability, and user experiences. The results are grouped by the level of difficulty, from level 1, which was low, to level 3, which was high. and the difficulty is based on model complexity and scale. The first part of data we examined was the patterns in how people use the system. This section is where we look at the three main themes of context switches, collaboration styles, and device handling. First, we'll look at use patterns and context switches. At first glance, you can see that there is a high amount of purple on this timeline. And just from this, you can see that there is a high amount of context switches across all groups. More specifically, there was over 1,500 context switches. Pairwise comparisons revealed that there was a significant difference between the third level of difficulty and the other two, showing almost double the amount of context switches. And on the comparison tasks, although the task completion times are generally larger, there are still less context switches and larger gaps between them. Moving on to device handling, it can be seen that over all levels of difficulty there was no significant differences. For device mobility in general, we observed very little frequencies of changes between orientation and also handling. It shows that most participants would hold their device in portrait mode even whilst completing other tasks such as writing notes. For each collaboration style category, we observed the following frequencies. It becomes immediately clear that in general, participants weren't sharing their devices. We can see the highest collaboration style was distributed view with discussion, which showed people have a focus on their individual devices. This was also backed up by the third most being distributed views with no discussion, where participants focused on their own device with no discussion. Pairwise comparisons between the first level and third in inspect tasks show that there was a reduction in collaboration style changes within groups. It also shows the less difficult model having more collaboration style changes, with participants looking through each other's devices and engaging in more active discussions. Similarly to the inspect tasks, pairwise comparisons show that there were also significant differences between the first and third level again in comparison tasks. However, there was also a significant difference between the second and third level, which shows that when comparing, the more difficult models had less collaboration style changes overall, with participants focusing on their individual devices. Overall, for use patterns, the video analysis shows diverse and changing collaboration styles, a high degree of context switching, and a decrease in collaboration for complex models. For usability, we wanted to find out if the increase of difficulty had an impact on their workload. We expected to find that as the difficulty increases, this would affect mental demand in particular. Upon first observation, over both task categories, the perceived load over all the metrics are high. For the most part, this is because a lot of multitasking is naturally involved with this collaboration, such as moving around, speaking to peers, and holding their phone just to complete one part of the task. Altogether, this means that there is a high perceived load. Looking at both task categories, the statistics show that there are significant differences in mental demand, effort, and frustration in both inspect and compare tasks. This shows that the abstract exemplars we provided were different enough in difficulty that when this level increases, it becomes more mentally difficult for the users to complete tasks, which is what we expected to happen. There was also a significant difference found within the physical demand section in the inspect tasks, which tells us that the different scales of the objects made participants more physically involved to view the models on their viewports. Overall, for usability, the NASA TLX data shows an overall high load, and significant differences across models for mental and physical load, as well as overall effort. We also looked at a qualitative perspective of how people use the system and how they appropriated the tools that they had been given. We observed that context switching occurred a lot when referencing locations of the virtual object. For example, one participant said, "the face closest to the researcher." We also observed it happening when participants wanted confirmation of a particular statement that they had said, or even in natural conversation. For example, when a participant addresses a particular person, they would glance at them. And although the third model had the least context switches, participants rated it as the most mentally demanding, saying if you got closer, you couldn't see both sides of the model, and it got more confusing. Which could be one reason for less context switches, as they didn't want to lose what they were seeing. We know that the most used collaboration style in each group was distributed view with discussion. Each user would focus on their own device whilst discussing a task rather than looking at other people. We also observe participants using their own device, but using their hands and words to play spatial signals to other users when discussing. For example, it is the side closest to the camera, and the user, whilst looking through their device, would signal spatially where they were looking. And while spatial referencing contributes towards coordination, our observations show that it is commonly used in AR-mediated collaboration as a workaround and replacement for direct face-to-face interaction. We expected that participants would change their orientation to landscape a lot to allow for more content to fit on the smaller form factor displays. What we actually observed is that participants decided to keep their phone in portrait mode instead of landscape. And when asked, one participant said, "I never really use my phone in landscape mode, it never crossed my mind to do that." If the models were scaled larger than the actual viewport, it could have been shown that more participants would have changed their device to landscape. However, when asked about this, one participant stated, "Sometimes it was difficult to concentrate on the larger objects because of the other things in the room, such as a TV and a cupboard." Our findings show that in handheld augmented reality, as intricacies and complexity of models increase, there is also an increase in mental demand, a decrease in the number of context switches, and a decrease in the number of collaboration style changes, which altogether shows that there is an overall reduction in group interactions. In the paper, we propose 5 different design recommendations which are directly grounded in the empirical findings of this paper, and oriented towards building applications and systems for collaborative work. For example, visual guidance, which would be a guidance mechanism to help users find their previous or a more appropriate view when they return to the model. Or with view filters, where we would remove the background clutter and noise from the physical space and allow a toggle between a collaborative and a full screen view. To conclude, AR is a huge technology which is making its way into the global market pretty fast. However, there are still a number of problems with this technology, particularly with face-to-face collaboration. For example, the sheer amount of context switches and the complexity of virtual objects. And there is an absence of clear collaboration mechanisms. Thank you for watching this presentation, and if you have any questions, please feel free to email me.